We're going to leave that last time. Okay, Ryan. Ryan, you're up. Tell me, what did you guys talk about besides something about university?
Well, you take the total radius of the circle, which is 360.
Okay, we don't know what that is though. So.
You know that the whole circle is 360.
Yeah, but how do you know what that is? So all you get is like a tape measure and a ruler and a pen and a string. That's all you get. So 360, we don't know anything about that. Who else had an idea? Adam.
Could you measure just like the circumference of your pizza with a string?
How would you measure it with a string? So tell me every step.
Take your string, just put it all the way around the outline.
All right. So we're going to take this. Is this making you hungry?
Yes.
All right. So should we do it on this pizza instead?
Yeah.
Okay. All right. So blue. Here I'm going to use a blue string, fitting, right? Okay. So you say I'm going to wrap that string all the way around.
Sure.
Okay. That's supposed to be around the edge. Okay. Then what?
Take the string away from the pizza.
Yep.
And then measure how long it is.
Straighten it out.
Put little marks on that pencil. Measure it alongside your ruler.
Okay.
And take a pen and mark your string to 9 equal different segments.
So take the length, divide by 9. Is that right?
Then you could, if you then take your string and you put it back around the pizza, and you make a little slice in the pizza on the outside of the pizza, wherever you have a mark on your string, you'll have 9 separate slices.
Okay. So then we could go back to a circle. So if we're doing the blueprint, then we'd have this thing right here that would be like 1/9. And so we could get our blueprint like that. So we would know then how to design that pizza cutter to get 1/9. Agree? Will it work?
No, you need to know what the actual is, though. Like, it's not going to be exactly about that same size.
Okay. Ryan, what do you think? Were you reacting to what he was saying?
I just think we were fine with that.
This will work?
Yeah.
So the theory is you take 1/9 of the string. You know what 1/9 of that string is? That's 1/9 of the circumference. That will give us a wedge if we use the center. That will give us a wedge that's 1/9 of the pizza. You don't think that works? Scott?
I think you need to know how deep to make the slice. You have to run another string through
the center of the pizza, measure that, and then find the halfway point to know where where the point would be.
The center.
Yeah.
So you're talking about locating the center.
Yeah, okay.
So we're assuming we can locate the center. Yeah, so if we had the center located and we wrap the string around and we got that 1/9 of the circumference, does that do it?
Yes.
Yes, does that do it? Naz, you okay?
Yeah.
Yeah, that does it, right? Because the 1/9 of the circumference is going to mark off exactly what the wedge is that would make 1/9 of the pizza, right? So this is our basis for angle. So what are we using as the basis for openness or basis for angle? Comes from what? The circumference of a circle, okay? Or the fraction of the circumference. Is that comments? All right. So this is our basis for measuring angles. So let's summarize that. Okay, so percent of or fraction of a full circular rotation. This is how we measure angles. So degrees doesn't come first. This comes first. This is our foundation for measuring angles. Another way to think of it is the circular arc length relative to the whole circumference. Again, a fraction, meaning a fraction of the circumference. Okay, so let's practice here. So here I'm showing you an angle. So if you put its vertex at the center of a circle, and then you look at what part of the circle gets cut off by the angle's rays, what fraction of the circle is what I've highlighted in red. That's, what fraction is that? 1/4. So we define that as the 1/4 angle, 25%. You know that as a right angle, right? So as a number, we can start by saying that angle is 1/4 or 25%. Okay? So put the vertex at the center of a circle. And then we ask, what fraction of the circumference is it? So, I tricked you, right? Trick or treat. All right? So the red, that part, what fraction of the circumference is the openness of that angle? 2/3. Or 67%, 66.7%. One more. Put the vertex on the center of a circle and see where the rays cut the circle. Tell me, so what angle is this? 1/6 angle, or 16.7%. So this is the idea behind measuring angle. It's the portion or the fraction of the circumference, or the percent of rotation, how much rotation you get. Or the arc length relative to the circumference. Arc length relative to circumference, so 1/4. So if the circumference is 4, we're taking one piece of it. If the circumference is 3, we're taking 2 of the 3 pieces of the circumference. So now we talk about degrees based upon this. So based upon this, what does an angle of 1 degree represent based on what we just talked about? Okay, so I can even zoom in if you want. So 30 seconds, talk to the person next to you. What is an angle of 1 degree based on what we just said? Go, what's an angle of 1 degree? Okay, Edward, tell me, what do you think?
So the total is 360, so it'd be
What is 1 out of 360? What are you looking at? What's that? Yeah, but what are you looking at that's 1/360th of what? Okay, right. So we look at that amount of arc length that's cut off right there by the angle, and you're telling me that amount of arc is what? Of? The angle that cuts off 1/360th of circumference, right? So it's the angle that would cut off if you put its vertex on the center of a circle. That angle would cut off or include exactly 1/360th of the circumference of the circle. Okay, so here's a nice precise definition. An angle with a measure of 1 degree, whose vertex is placed at the center of a circle, has rays that subtend an arc length, that's 1/360th, of the circumference of the circle. So in the context, you can kind of figure out what this word subtend means. It's kind of a helpful word to kind of shorten things a little bit. And they use it you'll see that. Subtend just means that the rays will include or cut off to include that much arc length. That's what subtend means. Cut out a piece, right? The rays cut out an arc from the whole circumference. So that's what subtend means. So define what an angle measure of 36 degrees is. What is an angle measure of 36 degrees? What would it be? Go. Talk about it. 36 degrees. Okay, where's Brian Sloan? Brian, tell me. So how would you describe what an angle of 36 degrees is? Oh, okay, Jackson.
1/10 of the circumference of the circle.
So the angle, so what is 1/10 of the circumference? So there's the angle, okay? So what's 1/10 of the circumference? What piece?
The arc length that you cut.
Right. The arc length that's cut by the angle would be 1/10 of the circumference. So the arc length that's cut from that angle, if you put the vertex on the center, is 1/10 of the circumference. So that's degrees. Okay. Help me. Where am I? I think we're here. There we go. Sorry. All right. So let's take a look at another way. So degrees is one way to measure angles, and we're seeing degrees as in terms of this idea of it's the percentage or fraction of the circumference. So here's another perspective on that. So here are 3 circles. Can you see the units on the axes? So what am I showing you right here? Does that show up? Yeah, good. So I got a pink bar here. What am I showing you by that pink bar? Radius, and what radius is it? Value. Can you read the scale? It's radius of 1, right? It's the scale of those 2, 4, 6, 8. So this I'm showing you, I'm highlighting the radius of the smallest circle, which the radius equals 1. Now watch what I'm going to do. I'm going to take that radius, and I'm going to pull it off its normal spot, and I'm going to keep its length and wrap it on the circle. Did you see it? I'll show it to you again. Burn this image in your mind. I'm going to take that radius off the conventional radius position and keep its length and wrap it on its circle. All right, let's do it again. So now what am I showing you here? Blue one. It's this middle circle, which has a radius of 4. Same thing. I'm going to pull it off its traditional spot and wrap it up on its circle. So it maintained its length. So what's the length of that arc still? Still 4, but it's wrapped on its circle. One more time. What does it show? Radius of 6, the biggest circle. Now I'm going to take that same length, turn it into an arc length on its circle. So I want you to answer the question, what are two things that are, besides the color, what are two things that are different about these 3 arcs? Different. So obviously the color is different. And 2 things that are the same about those 3 arcs. So what are 2 things that are different about those arcs, and what are 2 things that are the same? Go, take a minute. Where's Adidas? Is Adidas here? Okay, what about Yahaira? Tell me. Tell me something different besides the color. What's different about those 3 arcs? She said different lengths. Are they different lengths? Yeah, 1, 4, and 6. Different lengths. Right, so the length of each, the arc length is different. That's the main thing. Anything else that's different? Worth noting? Yeah. Okay, cool. So the radius of the circle that they come from, right? So that's the same as the arc length. But yeah, so they're each on a different circle of different radius. Cool. So now here's the more important thing. Taylor S. Shackelford. Something that's the same about those 3.
Each one is like a proportional length, like what it covers is the same proportionally.
Okay, so
The arc length is proportional to each. It covers
so the
same
fraction of the circle.
Right.
The fraction of the circumference is the same. Okay, does that have any relevance to what we're talking about? Yeah, why? So if the fraction of the circumference is the same,
The radius always covers a certain arc length.
okay? And so then what are we saying is, what are we basing fraction of a, yeah.
The angle is the same.
Right, so they're all marking off the same amount of openness, right? So, let's see here. So we need to make the definition here for our angle. So here on the x-axis, this is called the initial side of the angle. Okay, that's called the initial side. It's the positive x-axis. It's often referred to as the 3 o'clock position, because on a clock, you're pointing right at 3 o'clock, right at the 3. Make sense? So this note, you'll see this terminology a lot. This initial side of our angle is referred to as the 3 o'clock position. Okay? A positive opening angle then is opening counterclockwise, just like I'm showing here. So positive opening angle counterclockwise. Counterclockwise. Okay? And so then this, so here's that angle opening up, and so since all of them have the same fraction of a circle, they're all marking off the same amount of openness of an angle. And that's called the terminal side. So initial side is the 3 o'clock position, opens counterclockwise to the terminal side of the angle. And if we use the radius, we get the same fraction of the circle, so we get the same angle represented by all 3 of those radius lengths. Okay. What in terms of how can we see these as the same in terms of length? So the arc length is definitely different. This is 6 units, 4 units, and 1 unit. But there is a way that we can think of those lengths as all being the same. How is it that we can think of all those lengths as all being the same? Even though measured against the axis scale, they're different. But there's a way we can think about it that all those arcs are the same. G. But as a length. So as a length. Angelica. What's that? Specifically the length of those arcs. There's a way we can think about those all being the same length. Frank. No? Someone said it. It's the radius. So they're all how many radius lengths? 1. They're all. You can think of all these as 1 radius length, right? Because the pink one is the radius length of its circle. One of those. And the blue one is 1 radius length of its circle, and the red one is 1 radius length of this circle. So all of these are 1 radius length. And so therefore, we say this amount of openness is 1. Let's do it in blue here. So 1 radius length gives us an amount of openness of 1, anyone know what it's called? Radian. So radian is another way to measure angles. We talked about degrees. We talked about fraction of the circle, first of all, and then we talked about degrees. And so a radian is another way to measure the openness of an angle. What's it based on? It's based on how many radius lengths the angle cuts off. So for instance, I'm going to increase this to show 2 radius lengths. So now I'm for each of those circles, I'm laying 2 radii or 2 radius lengths. And so therefore, how many radians is that angle? It's 2 radians, because this openness in radians comes from how many radius lengths are cut off by the angle. So the angle I'm showing right now is 2 radians, which comes from the fact that it cuts off 2 radius lengths. Adam?
Can you describe that almost more, please?
So back here, what's the length of what's the length cut off? So this is all these arc lengths can be thought of as 1 radius. Do you see that? So because they're all 1 radius, the openness then, the corresponding openness of the angle, we say is 1 radian. So this is where radians come from. They come from the number of radius lengths that your angle cuts off. So if you cut off 1 radius, you've got an angle of 1 radian, angle measure. If you cut off, so here, down here at the bottom is showing you how many radius lengths. So here's 1.79 radius lengths, not quite 2. So this is 1.79 radius lengths. So this angle then is the openness of it is 1.79 radians.
Okay, so your arc length is 1.79 times the radius?
Yeah, but we can just call it 1.79 radius lengths. We can use the unit of radius lengths. And that way it's the same for any circle that you pick.
Okay.
Does that make sense? So every single circle that we put its center on that vertex, this angle will cut off 1.79 radius lengths,
Okay.
no matter what the size of the circle is. So we call that particular angle 1.79 radians. So then we had said 2. Here's 2. And then let's go all the way to 3. All right, so I'm showing you 3 radius lengths on all 3 circles. And what I want you to do is make a table. And in the table for the pink, and for the red, and for the blue, you're going to write down 3 things. What's the radius? This is our symbol for angle. It's theta. The symbol is a common symbol for angle. Specifically, this angle swept counterclockwise from the 3 o'clock position. You're going to hear that a lot. Swept counterclockwise from the 3 o'clock position. And then total arc length. So I'm showing you 3 radius lengths. 3 radius lengths swept counterclockwise from the 3 o'clock position. And so for each of the pink, blue, and red, you're going to fill in this chart. What's the radius, value of the radius? What's theta, the angle? And S stands for arc length. And then that S is in the units of our axes, in these units, 2, 4, 6, 8, 10. Is the task clear? Does it make sense what you're doing? I'm going to take attendance. All right, talk it out. Malenko, you're up. My pen. How's you doing that first, the pink? So in the pink one, what's the radius? We're going to regroup here. The pink. He said the radius is 1. What's that? That's a really weird arrow. Oh, I know what's going on. There we go. Okay, so the radius is 1. What's the angle in radians? How many radians is that? 3 radians. And what's the arc length in the units of our axis? How long is that? 3. Here's his answers for the pink. 1, 3, and 3. Agree? All right, cool. Red. So let's do the red one. Adam. Where's Adam Colhase? Right here. Tell me, for the red circle, what's the radius? Oh, sorry. I got them mixed up. Anyway, so let's go. It doesn't matter. So red, the red circle. 6. Angle. How many radians of openness is that showing, the red arc? 3. Okay, Okay, if you're talking about math, you can whisper, okay? And then what about the arc length? 9. Is the arc length 9? So how long is that right there? So if it's 3 radius lengths, and each radius is 6, try again, what should that be? So we get 1 to about here. So that's, how long is that right there? No, in the units of the axis, Adam. How long is that? That's 1 radius length. How many units long is that? In terms of these, so 1 radius length is how many units? No. 1 radius length. How long is the radius? No, the radius of the red circle you told me is 6, right? So if you go 1 radius length, how far have you gone? 6. And if we go 2 radius lengths, which is about to here, we've gone 12. And so then 3 radius lengths? 18. Make sense? Cool. All right, blue one, middle circle. Leah.
So the radius is 4.
Radius is 4. What's the angle? What's the openness? 3. What's the arc length? 12. Okay, so I want you to make a formula of r, theta, and s. How are r, theta, and s related? Go, write a formula.
Is the formula for data?
What's that?
The formula for data or for,
Formula that brings all these 3 together.
so it doesn't matter what you're solving for?
Yeah, right. Yeah, there's different ways to write it. You're right. So whatever's natural to you. So before we do that, I'm going to point out that this number in the middle column, we can think of that number in 2 different ways. We can think of it as the number of radians of openness, or we can also think of it as how? It's another way to think of that. Number of? Jonathan, number what? What else? How else can you think of that?
The radius by any number of radians will give you your length.
Okay, measured in what, right? It's length measured in what? What's the unit? We can think of that as length. And what's the unit of that length? Anybody? What do you think? Yeah, it's the number of, like, how many radiuses or how many radii. So it's the number of radius lengths. That's what I gave you to start with, right? I told you that I'm going to show you 3 radius lengths. Radians then is the same value, but radians represents the openness of the angle, whereas radius lengths is the arc length cut off. You see? But they're the same value. Okay? All right, so who came up with a formula between r, theta, and s? Who would say? Someone new. Yeah. Jonathan. S equals r theta. Agree? So what does that say? It says that what? The total arc length equals the length of the radius times. So now, which of these 2 kind of makes the most sense to think about when you see that? Does it make sense to think about the openness of the angle or how many radius lengths you have? Yeah, so in this formula, it kind of helps to think of it this way. Even though we're using the symbol for the angle, it helps to think of that theta as how many radius lengths, because it's the length of the radius times how many you have gives you the total arc length, right? See? So the total arc length is the length of 1 radius times how many of those radiuses you have, or how many radii or radius lengths you have. But it also is the number of radians, the openness. Okay, does it make sense? So did you want to do this different, Moises? This formula? Did you come up with a different formula?
I was just asking what you would solve for when you asked this for, but you could also do data equals arc length divided by radius.
He wants this. Is that right? So does it make sense if we take the total length of the arc and divide it by the length of 1 radius, what value are we getting then? Yeah, we're getting so it's like we're saying like if you have the total length of the arc and you divide it up into a certain length, you're saying how many of those do you have? How many radius lengths? And that's the same as the radians of openness. Okay. Can I erase? Does this make sense? So it's a really important formula, but not only just the formula itself, but what it means, like what's going on there. What's going on? That's why we built the table, and we're talking about that. Any questions? Okay, so let's zoom in. So then I'm showing you an openness here of, maybe, can get it? I can't get it in between. There we go. So this is, the pink arc now is 4 radius lengths, and so that is, shows an angle of 4 radians. Here's about 5. 5 radius lengths, openness of 5 radians. 6 radius lengths, okay, and so then a full rotation is something greater than 6. So let's actually talk about halfway around the circle. Let's see if I can have something here. Sorry, there we go. All right, halfway around the circle. So this is showing 3.09 radius lengths to get halfway, or it's not quite making it. You see that? So the question is, so the way I have this slider sketch, 3.09 is not enough radius lengths to get halfway around, and 3.19 is too many. Okay, so 3.19 radius lengths takes us further than halfway around. So it'd be very nice to know what is exactly halfway around. How many radius lengths does it take to get exactly halfway around? Something between, some number between 3.09 and 3.19. So, take a guess. 3.1415. Anybody know more digits than that? What's after the 9? 2? Someone said 2. Is 2 next? I don't know. What's after 2? Who really knows a lot more digits? Can tell me. 2? Are you making it up? Is that right? 654. All right, that's probably enough. All right, let's see. Look at that. Okay? Yes. So you've used pi, but many of you never knew what it was. What is the number pi mean? Pi is what about? So just to say it's a half circle. No, a half circle is like the arc. What is pi? Taylor. He said the number of radius lengths to go halfway around the circle. If you laid radiuses on the circle, that's how many it would take, 3 and 0.14, to get exactly halfway around. Okay? So then what about all the way around? 2 pi, right? 2 pi. Okay, so if pi is halfway, then all the way around is 2 pi. And why do we care about that? Because when we're talking about radians, these integer whole values of radians, what happened? Oh, here it is. Whole values of radians don't give us convenient places on the circle in terms of symmetry. They're important for our understanding of what is a radian, right? So, that's 1 radian, 2 radians, 3 radians. But then they end up just kind of in random type places in the circle. But if we know exactly how far halfway is, then based on halfway, we can get symmetric places. So therefore, what is what we call a quarter angle? A quarter is what in radians? It would be half of a half circle, or pi over 2. So pi over 2 radians is our quarter angle. It's our quarter angle. And so we can keep doing that. So based on pi, we can get nice symmetric places on the circle in terms of how much openness swept from the 3 o'clock position. Okay, next homework will be due Monday. I'll post it today.